When we discuss the elastic behavior of the lungs, there are two interrelated concepts that must be kept in mind. Number one, the compliance of the lungs. Number two, elastic recoil of the lungs. So what does one mean by the term compliance of the lung? Formally, the term compliance of the lungs is defined as the change in lung volume for a given change in the transmural pressure gradient, right? Colloquially, it may be defined as a measure of the amount of effort needed to distend or stretch the lungs, right? So a more compliant lung will need a smaller transmural pressure gradient in order to inflate it by a certain amount, whereas a less compliant lung will need a higher transmural pressure gradient to inflate it by a certain volume. Now, what is transmural pressure gradient? Transmural pressure gradient is the pressure difference between the alveolus and the pleura. So the difference between intra-alveolar pressure and intrapleural pressure. Transmural pressure gradient is the main force that keeps the lungs inflated alongside surfactant activity, right? So compliance is important for a lung to be inflated by a normal amount in each inspiration, right? And there are certain conditions in which the compliance is reduced, primarily pulmonary fibrosis, in which the tissue, elastic connective tissue, which is mainly responsible for the compliance, is replaced by scar forming fibrous tissue, and fibrosis happens secondary to a lot of conditions including tuberculosis and pneumonia. So this is it for compliance, and we do have compliance curves, and the compliance curves for inspiration and expiration is different, in which we basically have lung volume against the pleural pressure, right? Anyways, generally speaking, for a normal person during a normal respiratory cycle, the transmural pressure gradient during or at the start of inspiration is negative 7.5, whereas its value at the end of expiration is about negative 5. So the transmural pressure gradient changes by about 2.5 centimeters of water for the lung to expand by the normal amount for each inspiratory cycle. And for each inspiratory cycle, by what volume do you think a normal lung expands? Per respiratory cycle, per inspiratory cycle, the lung expands by a volume of 500 ml, and this is the tidal volume. When expiration begins, the transmural pressure gradient again falls from negative 7.5 to negative 5, and the change in lung volume is again of about 500 ml, just in the other direction. This is again how this works. Now this is it for compliance. And how does the transmural pressure gradient change? The transmural pressure gradient is actually changed by changing the intrapleural pressure, because it is not communicating with the thoracic cage or the atmosphere, so it will not equilibrate, thankfully, right? And how does the intrapleural pressure change? The intrapleural pressure can be changed, can be made more sub-atmospheric in order for there to be a pressure gradient existing. For this to happen, the inspiratory muscles need to do work. And the inspiratory muscles include the diaphragm and the external intercostals, and inspiration is largely an active process. And so when expansion of the thoracic cage happens by virtue of the action of the inspiratory respiratory muscles, the lung similarly expands because of the parietal pleura being in close contact with the thoracic wall. And so the intrapleural cavity is stretched and the intrapleural pressure decreases. That is basically how it normally happens. Now if you talk about the compliance of the lung, we mentioned it as 200 ml per 1 centimeter of water change in the pressure. However, it is for each centimeter of water change in the pressure, the thoracic cage expands by 110 ml. So the compliance of the whole thoracic cage is about a half compared to the compliance of the two lungs in isolation. This is compliance. Now if we talk about factors that influence the compliance, we talked about the transmural pressure gradient, and we talked about the nature of the elastic tissue. Another factor that influences the compliance is something known as surfactant. And surfactant is basically something that increases the compliance, and we will talk about it later. Now what about elastic recoil? Elastic recoil is something that is very important because expiration, in contrast to inspiration, is largely a passive process. At the end of inspiration, it is the passive elastic recoil that returns the lung volume back to its pre-inspiratory volume. So basically, when the stretching force exerted by the transmural pressure gradient is lifted. And how is it lifted? Because of the relaxation of the internal intercostal muscles, external intercostal muscles, and the diaphragm. It is the elastic recoil that returns it to its normal value. Alright, and this is for quiet expiration as part of a quiet respiratory cycle, so there isn't a lot of exertion, and elastic recoil is enough. The situation is a bit different in more strenuous breathing, right? So what are the properties of the lungs that give it the characteristic of elastic recoil? Number one, the elastin fibers present in the parenchyma of the lung. This is important, but the other one is more important, and that is alveolar surface tension. Within the alveolus, there exists something known as alveolar surface tension. Now what is surface tension? Surface tension is one type of force, and what does it exist and why does it exist? Surface tension normally exists whenever there is an interface between two states of matter, usually between water and air. The reason for this force is because whenever there is a water-air interface, we have a outermost layer of water. The water molecules in the outermost layer of water, they have strong cohesive forces in between the water molecules, whereas the attraction with the air molecules is much less stronger, and because of the unequal attractive forces, a surface tension, a force is produced that is directed inwards, perpendicular to the interface. Now what does this produce? This surface tension gives the alveoli a tendency to squeeze in on the air inside the alveolus and so collapse. So it is again elastic recoil. Right, now this is a bit of a normal process. In most attenuated expiration, we do need expiratory muscles, that is the abdominal muscles and the internal intercostal muscles, but generally speaking we don't need that. Now there is something known as a surfactant. When we normally talk about the surface tension at an interface between pure water and air somewhere outside the body, the surface tension is about 70 dynes per centimeter, and if this value of surface tension was to exist within an alveolus, the alveolus would collapse no matter the situation, and the reason for that is the alveolar surface tension would overcome the stretching influence of the transmural pressure gradient, right? Now if we are talking about the normal fluid that lines the alveolus inner epithelial surface, with the exception of a certain substance known as surfactant, the surface tension would still be huge, 50 dynes per centimeter. But if we talk about normal fluid lining the alveolus along with normal concentration of surfactant, the surface tension is about just 3 minimal, and this is quite manageable, right? So what is the function of this surfactant? This surfactant increases the compliance of the lungs and reduces the elastic recoil. How? Because the surfactant basically is a complex mixture of certain phospholipids, certain proteins, and certain ions like calcium. Now, one of its constituents, the most important one, is dipalmitoyl phosphatidylcholine, right? It intersperses between the water molecules at the outermost surface of the fluid layer, and basically the attraction between the pulmonary surfactant and the water molecules is much less than that compared to that of a water to water hydrogen bond attraction, and so the surface tension is reduced. Normally the surface tension tends to keep the surface area of the water surface at a minimal because it wants the molecules to be as close to each other as possible, and so this hinders alveolar expansion. But with the surface tension reduced, alveolar expansion is no longer hindered as much. Similarly, with the surface tension, which is a force, actually leads to the development of an inward directing pressure known as the collapsing pressure, which is responsible for a great deal of elastic recoil. So if surfactant basically reduces the surface tension, it basically ends up producing this collapsing pressure as well. Now this collapsing pressure, surface tension, it has a direct relationship with surface tension and an inverse relationship with the radius of the alveolus, right? Now these are all the normal situations. In certain situations, what if the surfactant is absent? In a condition known as newborn respiratory syndrome, uh, an infant is prematurely born, and because surfactant secretion by type 2 alveolar cells tends not to start until late into pregnancy, chances are that the surfactant concentration would be very less or would be altogether absent within the fetal lungs, within the infant lungs. So such a baby, the surface tension in the absence of surfactant would be quite high, and so the baby would have to exert a lot of inspiratory muscular efforts in order to inflate his lungs by the normal amount. Additionally, infant muscles are not that well developed, and this adds to the problem. And so if this is not treated heroically, death is an almost certainty. And how can treatment happen? By surfactant replacement and steroidal administration into the maternal blood at the time of labor to increase surfactant production, so the infant does have some surfactant when he or she is born. Because such a person would need a much higher transmural pressure gradient in order to expand lungs by the normal amount of 20 to 30 millimeters of mercury. This is the reason a much higher muscular effort is needed compared to a person with a normal amount of surfactant. Additionally, because in a premature infant, in any infant, the size of the alveolus is about 1/4 the size of the alveolus in a normal adult. This actually increases the collapsing pressure because the collapsing pressure is indirectly proportional to the radius and directly proportional to the surface tension. I'm hoping this is helpful.